This is Calculus Part 8 at the end of Part 7. Had a little slip of the tongue. I was saying that 2 divided by 4 is 2, and we all know that 2 divided by 4 is 1 divided by 2. So that's how we get from this step to this step. We just turn that 2 into a 1 and turn that 4 into a 2, and when you turn 2 into a 1 there's no point in writing it down, so we go from there to there. Okay, now if we back up a step, sorta. Okay, we divided r fourth by r, and we got r cubed. But let's go right back to having an r fourth on the top. Let's say torque equals stress max times pi times r to the fourth over, this is what we have here, except we multiplied that times r, so we'll put an r on the bottom also. So we'll put our r over here and our 2 over here. So this formula, this equation is the same as this one. We just multiplied the top and bottom times capital R. We still have our stress max and our pi at the top and our 2. We just rearranged them. And the purpose of that was so we can say that if we draw a circle around this part, that is defined as the polar moment of inertia. J is the letter we use for polar moment of inertia, equals pi r to the fourth over 2. Okay. So we can just say torque equals, let's leave that where we can see it, S max over capital R times J, the polar moment of inertia. Okay, remember our formula a while back? We said our bending moment, M, is equal to the stress. Okay, we can just go ahead and get rid of this S max. We remember that what we're talking about is the maximum stress in our shaft, like if this magic marker or this dry erase pen, whatever you call it, is a shaft, and we're torquing it, turning this and putting a torque on it. Well, the maximum stress is out there at the edge, and that's what this little s is. We use maximum stress in our equation to derive it to mean the stress out here. We used s to mean the stress anywhere between the center and the edge, but now that we've derived our equation, we'll just go ahead and get rid of the max part and just call it s, and know that we're talking about the maximum stress in our shaft. So, and back to our rectangular cross section, like our 2x4 teeter-totter board. Remember that the formula for bending moment was stress times the moment of inertia, I, over Y is what they called it on one chart. Sometimes they use the letter C. Anyway, this is the distance, this Y or C, whatever you want to put down here, is the distance between the centroid and the place where the stress is maximized. This I is our moment of inertia. This J is our polar moment of inertia. So bending moment equals stress times moment of inertia divided by the Z, by the Y or C, whatever you want to call it, the distance between the centroid and the maximum stress. So notice how these two formulas look so much alike. Moment, like torque, equals stress times a polar moment of inertia in this case, regular old moment of inertia in this case, and divided by the radius of the circle in this case, divided by half of the depth of the 2x4 rectangular cross section in this case. And we also said that moment of inertia divided by y is equal to the section modulus, so this m is equal to stress times z. Remember that formula, m equals stress times section modulus. We've seen that a few times. Okay, let's say we have an engine that's producing 47 horsepower. At 2,000 RPM. Okay, and it transmits this power through a 3/4 inch shaft. What is the stress in the shaft? Okay, let's draw us an engine here. That looked like an engine. There's a couple of jugs there. There's an oil pan. Okay, here's a shaft going to it, and here's a pump that looked like a pump. Okay, and this is a 3/4 inch shaft. Diameter is 3/4 of an inch. Okay, we know that a horsepower is 550 foot-pounds per second. 1 horsepower equals 550 foot-pounds per second. Okay, which means 1 horsepower is also equal to 33,000 foot-pounds per minute, because there are 60 seconds in a minute. Multiply that 550 times 60 and you'll get 33,000. Okay, so 47 horsepower is 47 times 550 foot-pounds per second, or 47 times 33,000 foot-pounds per minute. Let's multiply it out. 47 times 33,000 equals 1.551 million. Okay, add 1,551,000. Okay, a little over 1.5 million foot-pounds per minute. We know that 2,000 revolutions per minute equals 2,000 times 2 pi radians per minute, because 1 revolution, 360 degrees, equals 2 pi radians. So if we have us a circle here, let's draw us a diameter across here. Well, a radian's about 57.3 degrees. If we were to divide this in thirds, we'd have 60 degrees, 60, 60, but we're not dividing it quite in thirds. We're going to divide it in a little less than a third. Instead of 60 degrees, we're going to have 57.3 degrees. There's another 57.3 degrees. There's another 57.3 degrees. So, notice you have a little left over here. And 123.141592. Notice this is pi radians. Pi radians equals 180 degrees. Well, obviously 2 pi radians equals 360 degrees. And you remember the old formula, 2 pi r? Okay, well, a radian is defined as the angle, which is about 57.3 degrees, 0.3 something something something. It's a long, strung out number. But anyway, it's the angle such that this distance, this radius, distance from there to there, equals the distance of the arc from there to there. So, if you want to know how far it is around a circle, just say there's pi radians, and there's another pi radian, so 2 times pi times the radius equals the circumference. So if we have a shaft here that's turning 2,000 revolutions per minute, it's turning about 12,500 radians per minute, because 2,000 revolutions all the way around times 2 pi radians all the way around equals 12,566 radians per minute. Let's say we have our shaft here. Here's our 3/4 inch shaft, and here's a pulley. Let's say this pulley is a 2-foot diameter pulley. The reason we're saying that is because we want it to be a 1-foot radius pulley from the center to the outside. 1 foot. And let's say we got rope wrapped around it, and this pulley is lifting this weight. And let's say our shaft is turning 2,000 revolutions per minute, which we figure was 12,566 radians per minute. Yeah, there we go, 12,566. That's what you get when you multiply 2,000 times 2 times pi equals 12,566 radians per minute. So it'll pull 12,566 feet of rope per minute, because every radian that it turns, the arc length equals the radius, and the radius is 1 foot, so each radian pulls a foot. So it's turning 12,566 radians per minute, so it's lifting 12,566 feet of rope per minute. And we know that 47 horsepower, we figured a while ago, 47 horsepower corresponded to a little over 1.5 million, 1,551,000 foot-pounds per minute. Okay, well, if we're pulling 12,566 feet per minute, and we're doing 47 horsepower of work, or putting out that much power, which is 1.5 million foot-pounds per minute. Let's see, this would be feet per minute. Oops. Okay, we can figure out our weight. Our weight is equal to our foot-pounds per minute divided by our feet per minute. So 1,551,000 divided by 12,566 equals 123 pounds. Our weight equals 123 pounds. So 47 horsepower at 2,000 RPM corresponds to 123 foot-pounds of torque. Okay, now that we know the torque of the shaft, we can calculate the stress in the shaft. But it looks like we're about to run out of time, so we'll save that for part 9.